Swayam Prabha. Digital India. Educated India.
Welcome friends, today is the 10th class on GPS surveying. In this class I am going to discuss on errors in GPS observable. The systematic variety of error in GPS observable will be discussed. Now the content of this class will be like introduction, then followed by different types of systematic errors in GPS observable. There are 4 basic types: space segment error, atmospheric error, receiver error and other errors, followed by the GPS observable equations, which already I had discussed in the last class. Today I will just repeat it. Now as you know that GPS observables are endowed with errors. Different types of errors are present there due to different sources of generation of those errors, and the errors are fundamentally divided into 3 types, like gross errors, systematic error and random error. Of these errors, the systematic error are the errors which really follows some physical laws, so it is called systematic, and on the basis of the laws this may be modeled, which further can be removed from the GPS observables. So actually these errors have a very big deteriorating effects on the GPS positioning, so we need to know thoroughly about the different types of systematic errors and how they can be minimized or removed from GPS observables. Now on the basis of the source, the GPS observable contains 4 types of systematic errors. Now if we assume that the GPS signal is coming from satellites to a receiver, now while this signal is coming from the satellite to the receiver, it will pass through atmosphere. So now there may be errors in this signal which may be generated out of the space segment, that means related to satellites, they are related to orbit. Now as it travels through the atmosphere, there are different types of interactions of this signal with the atmosphere. So depending upon the type of interaction, there are 2 types of atmospheric errors. One is in the ionosphere and another is the troposphere. Apart from that, when it is coming to the receiver, there will be some errors due to around this receiver. So and apart from that there may be some other errors. So we can discuss like your space segment errors. There are 4 types. These are satellite clock error, then your ephemeris error. Satellite clock error, as the name itself understood, that it is the error related with the clock of the satellite. Actually the any satellite, any GPS satellite makes use of some atomic standard, and there may be lack in synchronization of the atomic standard with the GPS system time, and that is what is called satellite clock error. And this error may be removed or reduced by making use of some parameters which are available with the navigational message. So, actually as it is a systematic error, there is a standard model of its behavior, and that model is based on some parameters as well as some orbital parameters as well as some model parameters, and those values of those parameters are available in the navigational message. Now, the ephemeris error, from the name itself we can understand that it is related to the orbital motion of the satellite. As we know that the satellites are designed to move along certain orbital path, and those parameters are available in the navigational message, and that is called broadcast ephemeris data. But due to the extra gravitational forces like our sun pressure, there may be drift in solar drift and so many other things. So, these satellites do not or incapable of moving along the predefined orbit. So, there will be a difference between the actual position or actual orbital parameter and the navigational orbital parameter. So, that discrepancy arises, and that is called ephemeris error, and due to this error the position we do get from the broadcast ephemeris data will end up with some error in position. So, to avoid that thing we should go for relative positioning if the baseline length is small. Small means less than 20 kilometer, because in that case it is assumed that most of the ephemeris error or error due to ephemeris may be equal for the both station, and that may be cancel each other, or for long baseline we should go for precise ephemeris. Now, the next type of space segment error is satellite antenna error. Now, what is this? Actually, satellite is considered to be moved along the orbital path with respect to its center of mass, but the signals are coming and the range is being computed with respect to the antenna phase center of the satellite. So, there is a discrepancy between what we are computing and what actually it is. So, the difference between the antenna phase center of the satellite and the center of mass of the satellite, there is some certain values, and that may be taken into account while computing for very precise estimation of position, and the values are available in the IGS site, this one the available. So, this may be used to compute the errors as well as to remove the error from GPS positioning. And the last one among the space segment error is that satellite signal phase wind up error. Now, this is the error arises out of the axis of the antenna of the GPS satellite and axis of the antenna of the GPS receiver should be identical to, otherwise there will be some error in the phase measurement of the signal. So, this is also, these two errors are very minute, and specifically for very precise estimation of position, these errors should be taken into account. So, this is all about the space segment error. Now, after as the signals are coming from the satellite through the atmosphere, during the propagation of the signals through the atmosphere, the velocity of the signal as well as nature of the signal will be disturbed. Specifically, velocity will be reduced and the signal will get dispersed in the ionosphere and it will physically obstructed or deviated in the troposphere. So, all these things will make or provide some error in GPS observable and causing the error in GPS positioning. So, these error need to be addressed, has to be computed and then has to be removed from the GPS observable. Now, depending on the type of the interaction that the GPS signal will be undergone as will propagate through the signal, there are two types of error we do say. One is called ionospheric error or ionospheric error and the other is called tropospheric error. Now, for GPS, ionosphere is that part of the atmosphere which has significant amount of ions which will affect the propagation of the signal, because GPS signal is electromagnetic in nature and there is a layer of atmosphere varying from 70 kilometer to 1000 kilometer from the surface of the earth, which is having significant amount of electrons which cause dispersion in the propagation of the GPS signal. So, as it causes dispersion in the ionospheric GPS signal, the velocity of propagation of the GPS signal will vary. Now, there is a peculiar thing in this case, the ionosphere speeds up the carrier phase. So, the velocity of carrier phase gets advanced, that means it increases. Due to dispersion phenomena, velocity of carrier phase gets increased. So, as a result of which the carrier phase range measurement will be of less than actual, because velocity is increased means time of transmission will be less. So, the distance measurement or range measurement will be less than actual, whereas the code phase of the signal will be delayed and the range measurement will be more than actual. So, the effect of ionosphere on the carrier part of the signal is different from its code part. Not only the nature, but also for different types of codes, the amount of ionospheric error will be different for different types of signals. Carrier phase like L1 carrier phase, L2 carrier phase, L3 carrier phase, the effect of ionosphere will be different for each of these. Similarly, for CA code, for P code, for CM code or CL code, this effect of ionosphere will vary. So, and the effect of ionosphere on GPS signal is the worst kind of error that is available in GPS observable. So, it is very important to know the amount of errors due to ionosphere, and in fact we should, rather than finding out the errors, we should try to plan our observation in such a way so that the ionospheric activity is least, because ionospheric activity is maximum when the when it will depend upon the position of the sun, day of the time of a day, and the latitude of the place of observation, as well as ionospheric activity is in the upper atmosphere. Ionospheric activity chart is also available in the internet. So we should plan well, we should carry out well well before how when to take our observation, so that ionospheric action is less. Now that is one way how we can minimize the ionospheric error in GPS observable. First one is that planning, proper planning and observation schedule, and then because in spite of all our best effort, there will be ionospheric error in the GPS observable. Now next way to minimize the ionospheric error is to model it. Now some models are already available in GPS signal, GPS navigational data. We can make use of those model, and those model, by using those model, about 50% of the ionospheric error may be minimized. Still there will be some error, so for small baseline length we may go for relative positioning, that is also that will also provide some it will also minimize some error. Then we may go for some pre-processing operation. In the next class we will be discussing on those, and those pre-processing operations also minimize the amount of ionospheric error in the GPS observable. So in that way, under different categories, means different categories of operation as well as observation planning, observation, then pre-processing, all those steps will minimize the ionospheric errors in GPS observables. The next variety of atmospheric error is the tropospheric error. In case of GPS observation, the layer of the atmosphere where the signal gets physically obstructed, that part is known as troposphere, and it is about, you can say, 40 kilometer, up to 40 kilometer from the surface of the earth, and the tropospheric error are caused due to the temperature, pressure, humidity and their variations. So apart from particulates, so temperature, pressure, humidity and other particulates, their presence and their variations will may cause the physical obstruction of the transmission or propagation of the GPS signal through the troposphere, and also it will deviates. So there are two types of effect. One is the change in velocity, or we can say reduction in velocity, and change in direction. Change in direction means thus. So tropospheric error will cause always delay in propagation. So it is always, it will provide more range than actual, so it is additive in nature, always additive, and moreover it is same for code and carrier part of the signal. So the code part and carrier part of the signals will be having same tropospheric error, different types of code, different types of carrier will be having same amount of tropospheric error, and these are positive in nature. Now in this diagram you can see it is shown, if the signal is coming from the satellite to the receiver, instead of coming along the line of path, this is the geometrical path, they will take something like this due to obstruction as well as due to, and this is what is called refraction of signal, and also the velocity will be changing depending upon the density of the atmosphere. So as the velocity is decreased as well as the path is increased, the time of transmission will be more and the computed range will be more than actual, so the error is more, so correction has to be taken out. So this is what about the tropospheric error. Now because of this, now tropospheric error also can be modeled. Now some of the whatever precaution during planning that we have taken in we should be taken in during planning, some relative positioning can be done for removing some errors, some pre-processing techniques can be applied to reduce or minimize the error. Over and above, the tropospheric error may be minimized or removed by developing some models. And now one thing is important in case of troposphere, that the troposphere is very much site specific. So to deal with tropospheric error, it will be wiser to have a site specific tropospheric model. Now this with this I can go to the next type of errors, that is error that is around the receiver, GPS receiver. Now let me discuss about the third category of the systematic errors, that is the systematic receiver errors. Under this there are three types of errors we will be discussing. The first one is called antenna offset error. Now what is this? Actually the antenna of the receiver, there is a point called electrical phase center, and this electrical phase center is different frequency of the signal as well as for. Now this theoretically there is one point, but practically this point will vary depending upon the signal strength, intensity, field condition, etc. So as a result, the parameter called PCB, that is the difference between the EPC and physical antenna physical center. This is a parameter which is used to compute the height of the instrument. So if there is a variation in this, that means there will be errors in measurement in this for each observation, for each epoch of observation, and that will come into the height of the instrument, that means in the height measurement of the GPS position. So antenna offset error is an important parameter to be considered, while specifically we go for height measurement, and that can also be reduced by relative positioning or by making use of same type of instrument in all observation. That means in a campaign agar if we have 2-3 receiver we want to use, for each receiver we need to use same type of antenna, and the orientation of the antenna has to be maintained same. Next one, which is the most important of all errors, that is the receiver clock error. As we know that the receiver, GPS receiver make use of quartz clock, whereas satellite use atomic standard, and also our GPS system time, also GPS system time is also based on atomic standard. So there is a large discrepancy between the quartz clock of the receiver and the GPS system time. As a result, there will be a huge error that will be introduced in GPS positioning due to the receiver clock, and the error is such a great that whole of GPS positioning will be spoiled if we do not take care of it in the beginning itself. So the error due to GPS receiver clock is to be considered as an independent unknown parameter which we go for competition during positioning, and it is considered as the fourth unknown during GPS positioning. But though it is termed as the fourth unknown in the GPS positioning competition, but this is the parameter which has to be computed first. So if we get signal from only one satellite, we do go for measurement or computation of this error, and this is the most important unknown which has to be computed of all in the beginning. And the another variety of error which is important, that is called receiver hardware error. Receiver hardware error. So these are the errors which are associated with the malfunctioning of the hardware, and by taking a good variety of hardware we can take care of this. Now one of the two more, other than that there are two important errors which is to be taken into account, that is, one is called multipath error. Actually multipath error is caused due to presence of some trees or building or trees around the GPS observation. So what will happen, signal will first come to the tree and then it will reflected to the, or signal will come from the building and then it will reflect it. So along with the direct signal also some reflected signal will come to the antenna, and that is called, and the error caused due to this reflected signal is called multipath error, and this the amount of multipath error will vary from carrier part and code part, that it will be defined for both carrier and code, and the worst affected is the CA code, and because CA code positioning is the first positioning we have to determine, after which we go for very precise measurement. So if there is error in CA code positioning, then there will be end up with a very bad solution. So we should take care of multipath error, and the best way to take care of multipath error is to plan properly, so that our receiver is not placed in a crowded area, or it should be, we should if there is a cloud, then we should take the cutoff angle beyond that cloud. So that means cutoff angle should be taken more, maybe 25 degree, sometime maybe 30 degree, and also we should make use of antenna which is, and it will take care the multipath. So that is called multipath resistant antenna, or we should go for some receiver which is embedded with multipath mitigation technology, or we should go for some signal processing techniques which is also take care of multipath error. Another error which is important, that is called cycle slip. This error will come if there is some obstruction in the signal, or there is interference on the signal. Then what will happen, the number of cycles of, that means if we plot the integer ambiguity, then we will see that with time this, if we plot the phase observable, then we will get a scene like this. That means at this point the signal got lost and then again started after some time. So we need to identify this time, and we have to find out what is the amount of jump in number of phase cycles, and that has to be identified, removed, rectified as the pre-processing. And this can be taken care of by through pre-processing, and our many commercial software provides us the flexibility to process this data and remove the cycle slip. Incidentally, the cycle slip occurs only for carrier phase measurement. So this is what we can show about the cycle slip. And so with these different types of errors we have discussed, so finally all this will be taken into account, can be taken into account in under GPS observable equations, which already I had discussed in the last class, that the pseudo range observable is equal to geometric range. This is the error due to receiver clock, this is the error due to satellite clock, ionospheric error, tropospheric error, this is the error due to receiver hardware, this is the error due to satellite, and this is the multipath error, and this is the random error. So in that way, pseudo range which we will be getting from GPS observation, actually it will consist of so many errors, and this is the actual thing, that means this is the geometric range which we want to find out. Similarly for carrier phase observable, this is the geometric range, this is the integer ambiguity, this is the receiver clock error, this is the satellite clock error, this is the ionospheric error, tropospheric error, receiver hardware error, satellite hardware error, multipath error, random error. However, though the symbols are same, the amount of errors will be different. So with this I want to conclude today's class, and the summary of today's class may be like this, that GPS observable contains many systematic errors. Of these the most significant and important error is that our receiver clock error, which we take as the unknown parameter while computing the GPS positioning, that is to be done in the beginning itself. Next worst variety is that ionospheric error, which varies from signal to signal, different components of signal, and it can be minimized through proper planning and modeling. And the next variety is the multipath error, which has to be removed or minimized. Thank you very much. See you again in the next class. In the next class I am going to talk on GPS data pre-processing. Thank you very much.